I am Aniket Koul, and today we'll be discussing the 25th problem from the CP-31 sheet by TLE Eliminators under the 1200 problems. So now I'll be moving to the CP-31 sheet, and we can see that the 1200 parameter has been checked. I'll be scrolling down to find my 25th problem, and the problem name is same differences. Let's begin. The problem statement is as follows. You are given an array of n integers. Count the number of pairs of indices I, j such that I is less than j and aj minus ai is equals to j minus I. Now the input format is as follows. The first line of each test file would contain a single integer t denoting the number of test cases, and this number can go to 10 power 4. The first line of every test case would contain a single integer n denoting the size of our array, and it can go up to 10 power 5. The second line of each test case would contain integers a1 till an denoting the values of our array. It is also given that a of I would be between 1 and n. It is guaranteed that the sum of n overall test cases does not exceed 2 10 power 5. Now in the output you have to print a single number denoting the number of indices I, j such that I is less than j and aj minus ai is equals to j minus I. Right. Now, as we have seen the problem statement, we can move on to understand it. So we are given for every test case two things, n and a. N is an integer denoting the size, and a is an array of size n. Right. Now it is given that you have to find number of pairs of indices I, j such that I is less than j. This is the first condition. Also, aj minus ai equals, this value is equals to j minus I. This is our second condition. Now we have to find all the pairs of indices I, j which satisfy both these conditions, right? And we have to print that number. So let's see a sample case to understand the problem better. Let's take this case, for example, the first one. So let's paste it here. Right. I'll also increase the font size so it is visible better. Now in this test case, this is our n and this is our array A. Right. Now we have to find some pairs I and j such that it follows these conditions. So let's try to think. So as we don't have an algorithm, we have to just try to brute force and observe if we have any such pairs. So let me write the indices and the array so that it is easily understandable. 3, 5, 1, 4, 6, 6. This is our array and the indices are 0, 1, 2, 3, 4, 5. I'm using zero base indexing here. Okay. And even if you use zero based or one base indexing, this will not change, and we'll prove that when we come to the solution. So let's try to think for what values will it be same. So if we observe that these two, if they are I and j, then a of I equals to 4, I equals to 3, a of j equals to 6, and j equals to 5. Now a of j minus a of I equals j minus I. We substitute the values here, that becomes 6 minus 4, equals to 5 minus 3, and that is 2 is equals to 2. So this equation is being satisfied. So I can say the I comma j pair, that is 3 comma 5, is one of the pairs. And if we check carefully, we will not be able to find any other pair apart from this 3 comma 5 which satisfies both our conditions. So in this case, our answer would be 1. And if we check it with the answer given, yes, the answer is indeed 1. So this is our problem. Let's discuss the expiry time complexity. So if we see the problem carefully, there is a bound over sum of n over all test cases. So we know that sum of n over all test cases is less than equal to 2 into 10 power 5. So instead of writing our time complexity of the form t into some function of n, we would write it as O of f of n, because n itself has a bound over all test cases. So let's see. First of all, we need to know what is the upper limit of the number of operations, right? So on Codeforces, this value is around 10 power 8. That means we can run approximately 10 power 8 elementary operations in 1 second. That is good to go. Now, if this was O of n, then it would take around 2 into 10 power 5 operations, right? This would run pretty well. If we had n log n, now this is base 2, we should remember. This value would be 2 into 10 power 5 into 20, because log base 2 of 2 into 10 power 5 is approximately 20. So this is 4 into 10 power 6. This would also run pretty fine inside the 10 power 8 time limit. But if we go O of n square, then this value would turn out to be 4 into 10 power 10, and this cannot run, right? Because our bound is 10 power 8 operations. So we want some algorithm which runs in the vicinity of O of n or O of n log n time complexity. Now, as we have discussed the expected time complexity as well, we can move on to the solution. Now, the solution to this problem is quite fascinating. So let's rewrite the equation given in the problem statement. A of j minus A of I equals j minus I. Now, just looking at this equation, it is quite difficult to come up with any algorithm that would be easily able to solve this, right? Because as of now, we can only think of a brute force O of n square loop, where I loop over all I and j, and all those ij which satisfy this condition, I keep incrementing my answer and print it. So that is O of n square, but that won't run, right? Because we have seen it here, this won't run. So now let's do one thing. Let's shuffle the terms to the left and right hand side of this equation and rewrite it as following. A of j minus j equals A of I minus I. So what I have done basically, this A of I has gone to the RHS and this j has gone to the LHS. That's it. And these two are basically the same equation. Just shuffle them, right? Now you may ask, how does this equation help us in optimizing our O of n square solution? Let's see. Now what I do to my original array A, so this is my array A from, so as I've used zero-based indexing here above while explaining my sample case here, so it will be better that I use zero-based indexing here as well. So A0, A1, A2, so on till A of n minus 1. This is my array A. Now I rewrite this array also into the form A0 minus 0, A1 minus 1, A2 minus 2, A3 minus 3, so on till A of n minus 1 minus n minus 1. Right. I have changed this array in this form. Now let's see how does these two operations, changing A of I to A of I minus I and changing our equation into this form, how these two operations correlate. So now what I'll do is I will store this information inside a map. So I'll create a map. Let's say it is MP, and mp.first would store value. Okay. And this value is a value in this array, this new array. Let's call this A dash, right? So this value would be A dash of some index, right? And mp.second would be the occurrences, or if I say number of occurrences of this value that is stored in dot first. So this is how I store information in my map. And now let's see how does this help. Let's say in this new array A dash, I had two fives. So I had a 5 here and I had a 5 here. What does this mean? This means that if this is index I and this is index j, as A dash of index is equal to A of index minus the index, that means if A dash of I equals to 5 and A dash of j equals to 5, this also means that A of I minus I is 5 and A of j minus j is also 5. Now, as the RHS are equal, I can say that the LHS is also equal, right? So I can say that A of I minus I equals A of j minus j, which is basically the equation that we wrote here. And if you want to go one step further again, I can rewrite this as A of j minus A of I equals j minus I. So what I do is I bring A of I here and I bring j there. So this is the same thing. And this is the equation which was given in the problem statement. So this proves that inside the array A dash, in the new array A dash, if two indices I and j have the same value, that is, if A of I is A dash of I is equal to A dash of j, then in the original array A, it would satisfy the condition that A of j minus A of I equals to j minus I. These are one and the same, right? So I have proved the congruence between these two equations. Now, another small thing that I stated earlier, that I said that even if you take zero based indexing or you take one based indexing, this equation won't change. And why do I say that? Let's see. So let's assume for a fact there that we have zero based indexing here, right? So if I had to convert it into one based indexing, what would happen? So let's say if I had I equals to 2 and j equals to 4 in zero based indexing, right? So my equation would be a of 4 minus a of 2 equals 4 minus 2, right? Now let's say I write them in one based. So I would be 3 and j would be 5, right? And this is one based. Nothing else changes, right? So just converted zero based into one based. So my equation would look something like a of 5 minus a of 3 equals 5 minus 3. Now this value is equal to 2 and this value is also equal to 2. A of 5 and A of 4 are the same thing because this is one based indexing and this is zero based indexing. Similarly, A of 2 and A of 3 are the same thing. This is one based and this is zero based. And the RHS is also the same. That's why I say that either you choose zero based indexing or one based indexing, it is one and the same. Now, keeping this thing aside, we have proved the congruence between a of I equals a dash of I equals a dash of j, and a of j minus a of I equals j minus I. I have proved the congruence, but how does this help me to calculate the number of such pairs? Now, here is the place where the map comes into picture. So, as I said, the map stores the pairs of a dash of some index, comma its frequency, the number of occurrences basically. So let's say a value, imagine 5, occurred 6 times, right? Or even simpler approach to say that, let's assume a dash is the array 5, 5, 5, 5, 5, 5. So you can see there are 6 fives in this array. This is A dash, right? Now, what would A be? Could you deduce from there? Because A dash of I equals A of I minus I. So my A would be 5, 6, 7, 8, 9, 10. Assuming that I'm using zero-based indexing, right? So I have to now find the number of pairs, right? But I know that any I or j you choose. So in this case, any I and any j would result in satisfying the two conditions mentioned in the problem statement, right? So if there are 6 numbers and I can choose any two numbers, how many ways are there? What are the number of ways? This sounds very familiar, right? Let's generalize it. Let's say I have uh, let's use a better variable x. So I have x numbers and I want to choose exactly two numbers from the set of x numbers. What are the number of ways? What are the number of ways? Isn't it NC2? Try to think of it. Because we have to, sorry, it is not NC2, it should be XC2 because there are x numbers, XC2, right? Why? Because out of x options, I have to take 2, right? And the order does not matter because always I should be less than j. So I comma j and j comma I will not be two different pairs, right? Because j comma I won't satisfy if I comma j is satisfying, right? This should be clear. That's why we use xc2 and not xp2, because if both I and j comma I would be valid, then we would use xp2 because the order matters. But here, as I should be less than j, then only one of them would be valid. That's why I use xc2. And what is xc2? If we can expand it, it is simply x into x minus 1 by 2. Right. So now what our algorithm comes out to be, it is pretty simple. We create our map, this map of int comma int. Before this, we create our a dash from our array a, initialize this map mp, store the frequencies of the values of a dash here, and then for every key in this map, we take the value. So value is basically the frequency. And let's say the frequency is x. So I add to my answer xc2, which is equals to x into x minus 1 by 2. This is my whole algorithm, and at the end I print my answer. So this is how our algorithm turns out to be. I hope this is clear, and now we'll discuss the time complexity of this approach. So We are using a map here to store the values, right? And the map can at max contain n different keys, right? N different keys, because there are n numbers in my array A. So I can have at max n different values in A dash at max, right? And if there are n different values in A dash, then there would be n different keys in my map. And we know insertion in map takes log of n time, where n is the size of the map. So therefore, the map can go up till O of n log n time, right? And creating the array A dash is just O of n, because you have to just run a simple loop. So the total time complexity would indeed come out to be O of n log n. So now we have discussed the solution and the time complexity. Let's move on to the implementation. The implementation is quite simple, just repeating what we have just discussed. So for every for just we first of all we take the number of test cases as input, and then for every test case we take an input, the size of our array, and then we take in the array as input. So this is O of n. Also remember that while taking in the input, I am changing it into A dash, because nowhere in the algorithm we need the actual array A. So to save space, I won't be creating a new array A dash. I would be changing it on the go. So how am I changing it? I'm taking the input and then v of I minus equals to I. So that creates, so if this is A, then this creates it to be A dash. This is simple. O of n time. Declare a map named as frequency. So this will store the frequency of all values. Now I just run a simple for loop to update the frequencies of my A dash vector, right? Because now this was, if this was originally A, then now we can say that A has changed to A dash. So this is basically storing the frequencies of the values in A dash. Also, this loop can take up till O of n log n time, as I said, because insertion map is log n complexity, and if we have n different keys, we can go up till O of n log n time. Now we create our answer, and then we iterate through our map, and for every key, we do the xc2 for every value, right? So my value, so this is key and this is value. Count is the frequency dot second. So count into count minus 1 by 2, which is basically xc2. If I write here xc2 as I discussed in my explanation, and we keep adding it to the answer, and in the end we output our answer. So the total time complexity comes out to be O of n log n, because as stated earlier, we have a bound over sum of n overall test cases, so we won't be including t. And finally, also the total space complexity would be O of n, because we are just using linear space. So I hope you have enjoyed the problem. And for the ending remarks, I would say that the problem was uh, quite unique, utilizing the shuffling of variables in an equation, and these type of problems quite help you in thinking out of the box. Also, the combinatorics part was quite important after coming to the observation that we have to change a of I to a of I minus I. So these two, the combination of these two observations made this problem quite fascinating and helpful. So thank you.